So this is the microwave catalytic membrane for PFAS degradation. My name is Jeffrey Luke, and I'm an undergraduate student at NJIT. I'm currently working with Dr. Wen Zhang, Fangzhou Liu, Krishna Sai, Courtney Potts, Samuel Solomon, Ashish Kokula, and Hamza Abduli. Per- and polyfluoroalkyl substances, or PFAS, have been widely used in an industrial and commercial field. The concentration in water body ranges from a few parts per trillion to parts per billion levels. The concentration in human blood is 2 parts per billion at average. And their resistance to degradation is due to a strong carbon-fluorine bond. And finally, they are very toxic to humans. Microwave radiation enables fast, non-contact, and selective heating. It is also transparent for specific materials like polymers. However, what is the most important is the non-thermal effect. It is reported that the non-thermal effect of microwaves, such as the electrical effect, magnetic effect, and chemical effect, greatly increase the formation of hydroxyl radicals due to the excitation of hydrogen peroxide molecules to higher vibrational and rotational energy levels, which is able to enhance catalysis, promote the formation of radicals, and induce the microwave Fenton-like reaction. As you can see, when we turn on a microwave, the light bulb lights up. We can see a wireless transfer of electricity. With the popcorn kernel, we can see a contactless transfer of heat, which builds up thermal energy in the popcorn and causes it to pop. But you probably don't know what will happen when we combine the microwave and membrane together. First, we will coat the ceramic membrane with a microwave responsive catalyst, and here we use bismuth ferrite. Then, under the microwave radiation, the catalyst is able to promote the conversion of hydroxide to hydroxyl radicals, and the high-energy radicals can oxidize the PFOA and achieve PFOA degradation. Meanwhile, the microwave also is able to generate nanobubbles, which can deal with membrane fouling by adsorbing charged surface substances. This is our project design. This is the PFOA and this is the hydrogen peroxide. They lead to the same tube, which represents the contaminated water, which goes into the microwave and into the membrane filtration unit. This is the metal catalyst coated membrane, and that will go into here. Here we have the different power levels of microwave strength that we can test for. This is the outlet tube that will go into a beaker where we will test for PFOA concentration. The other outlet tube leads to a pressure gauge, which we can test for pressure. For the pristine membrane, or the red line, the removal of PFOA is negligent. But for BFO-coated membrane, the PFOA concentration dropped and progressively increased as the adsorption reached equilibrium and PFOA started to penetrate the membrane filter. The green bar represents when the microwave is on, and the microwave Fenton-like reaction contributed to PFOA removable rates of approximately 65.9%. And the LCMS was used to determine the PFPEA, or perfluoro N-pentanoic acid, which may be one of the intermediates of PFOA degradation, as its concentration increases under microwave irradiation. Our future plans are to firstly create a novel microwave responsive catalyst, which are non-harmful and stable, then to optimize microwave membrane systems for effective penetration of microwave radiation by using COMSOL multiphysics. Next, to explore the mechanism of interface microwave catalyzed reaction, and finally, to use MS2 bacteriophage, which will be used to examine the antibacterial and antiviral activity of functionalized membranes. Here are our conclusions. BFO-coated microwave-enhanced membrane filtration system was designed and operated. More novel anti-dissolving, low-toxicity composite materials will be synthesized and evaluated as potentially efficient microwave responsive. The microwave catalyst coated ceramic membranes filtration system will be further optimized with COMSOL multiphysics modeling. The microwave catalytic mechanism will be further explored by the detection of reactive oxygen species, or ROS, and nanobubbles. Antibacterial and antiviral activity of functionalized membranes will be examined. Thank you for watching.